This is an introduction to the first part of Lesson 9.1 regarding correlation and regression. And in this video, we want to focus on the following learning targets. We just want to give you an introduction to what linear correlation really is and what it represents. Identify the difference between independent and dependent variables and look at some types of correlation. And then we're going to actually learn how to calculate correlation coefficient by hand, which I'll forewarn you is a rather tedious calculation. So correlation basically just measures the relationship between two variables. And so when you've got a really strong correlation, that means that the two variables are highly correlated or they're related to one another. They're having an impact on one another. When you have a really low correlation, and we'll talk about what's high and low, that means there's not much of a relationship between those variables at all. So there have to be two variables when we're looking at correlation. So the first variable is, of course, the x variable. In algebra, we typically refer to it as the independent variable. In statistics, we like to refer to it as the explanatory variable. The y, on the other hand, in algebra, we typically refer to it as the dependent variable, but in statistics, we refer to it more often than not as the response variable. So we believe when two variables like x and y are strongly correlated, we believe that x is doing a great deal to help explain the behavior of the y variable. So here's an example of a set of data that is just a basic generic set of data, x and y coordinates. So you've got the ordered pair 1, -4, and that's this point here. And then you've got the point 2, -2, and that's this point here, and so on. Well, when you look at the arrangements of those points on this scatter plot, you notice there's a very noticeable pattern, okay? And that pattern is that there appears to be a straight line relationship or linear relationship between the variables. So if we were to calculate the correlation coefficient here, we'd find that they have a very strong correlation. They're highly correlated. There's a relationship. Knowing the value of x can help to explain a potential value of y that it would be paired with. So here are some scatter plots displaying some relationships between x's and y's. The one here on the top left is a negative linear correlation. It's negative because as x is increasing, the value of y is decreasing. Whereas the one on the top right here has a positive association, and it's linear as well, looks like a straight line pattern, and it's positive because as x gets bigger, y gets bigger with it. Well, down here on the lower left, those points just seem to be randomly scattered all over the place on the scatter plot, and there doesn't appear therefore to be any type of correlation at all. Whereas displayed here on the bottom right, we see that there is a U-shaped pattern to those points on the scatter plot. So there's a correlation, but it's definitely not linear. So those are some different types of correlations. You can have a positive or negative linear correlation. There can be no correlation whatsoever, or like the one in the bottom right, there's a very noticeable non-linear pattern, but rather U-shaped in this case. So we're going to take a look at this set of data. We've got a set of data that shows the relationship between the gross domestic product, the GDP, and carbon dioxide emissions, measured in millions of metric tons, whereas the GDP is measured in trillions of dollars. If we were to plot the GDP on the x-axis and the carbon dioxide emissions on the y-axis, we'd get a scatter plot that looks something like this. And there clearly appears to be an association because there's a pattern. As x is increasing, y is increasing with it, and it seems to be somewhat of a linear pattern. So we would say that there is a positive linear correlation between gross domestic product and carbon dioxide emissions. Now here's where the tedious calculation comes into play. When you want to calculate the correlation coefficient, there are all sorts of values that are factored into this calculation, all sorts of sums. You need the sum of the x's, you need the sum of the y's, you need the sum of the product of the x's and y's, you need the sum of the x squareds and the sum of the y squareds. What we have to do when we're calculating the correlation coefficient is we have to calculate all these sums. And later in this lesson, we're going to learn how we can use our sample correlation to try to identify whether or not we have evidence of a correlation in the population of all x's and y's that this sample comes from. So we're going to do this with a set of data here in a moment, but I want to talk about the values that correlation coefficient can have. It has to be a number between -1 and +1. When you have a correlation of -1, that basically means that there is a perfect linear association between the x and y coordinates. They all fit perfectly on a straight line, and that straight line has a negative slope. Whereas when there is a correlation of +1, that means it is a perfectly positive association. All of the points fit perfectly on a line, and it has a positive slope. A correlation of 0 means there's no association whatsoever, no linear relationship. So really, correlation measures the strength and the direction of the linear relationship between the two variables. Clearly in that middle scatter plot, there's no association whatsoever. So there's no strength or direction to that set of data, which is why the correlation is 0. So the closer correlation is to 1 or -1, the stronger the association, linear association. The closer that correlation is to 0, the weaker is the linear association. So when we're calculating correlation coefficient, as we said, we've got to get all sorts of sums. We've got to get the sum of the x's, the sum of the y's, the sum of the product of the x's and y's, the sum of the x squareds, and the sum of the y squareds. And then look at this bad boy. This is how correlation coefficient is computed. Okay, now I've calculated all these sums for you in this example, but I know that in MyLabs Plus, by the way, I'm having trouble logging into it this morning. I hope you aren't, but I know that MyLabs Plus is probably going to talk you through each of these steps. Calculate the sum of the x's, calculate the sum of the y's, and so on, and then plug them into the formula appropriately. So here's this data with regards to the gross domestic product and the carbon dioxide emissions. And we're going to calculate first the sum of the x's. We're basically just going to add up all of these GDPs that are provided for us in the set of data. And then we're going to add up all of these carbon dioxide emissions. Then we're going to multiply them together and add up those products. Then we're going to take each individual value of x, square it, so square 1.6, square 3.6, square 4.9, and so on, and then add those up. And then we're going to take each of these values of y, square 428.2, square 828.8, square 1214.2, and so on, and add those up. All of these calculations are necessary to compute correlation. So I did this for you. So the sum of all of the x's you see displayed at the bottom is 23.1. The sum of all the y's is at the bottom of that column. We multiplied 1.6 by 428.2 and 3.6 by 828.8 and so on to get these values in this column and added them up. Then we squared 1.6 to get this value. squared 3.6 to get this value, and added them up to get the sum of the x squareds. And then finally, I squared this value to get this y squared, squared 828.8 to get this y squared, and so on, and then added those up. So I have displayed all of those sums here on this slide. Okay? Now, the fun part. We need to calculate the correlation coefficient. So here's how we do it. Looking at this formula displayed here, we notice that on the top, the first thing is n. N is the number of pieces of data. Well, we have 10 ordered pairs. I shouldn't say number of pieces of data. I really should say number of ordered pairs. So it's not 20, but rather 10 ordered pairs. Then the formula says to multiply that n by the sum of the xy product. Well, the sum of the xy product is this guy right here. So I'm going to multiply 10 by 15,573.71. Then it says we need to subtract, and then we see the sum of the x's. The sum of the x's is this value right here. So I'm going to subtract 23.1, but that needs to be multiplied by the sum of the y's. And the sum of the y's is displayed right here. So that needs to be multiplied by 5,554. Okay, so there's the numerator portion of my correlation coefficient calculation. Now in the denominator, first I notice I have an n again, so 10, and these are all under a square root. That needs to be multiplied by the sum of the x squareds. So the sum of the x squareds I see is right here, 67.35. Then I need to subtract the sum of the x quantity squared. Well, the sum of the x is 23.1, and I need to square that sum. That, we notice then, is multiplied by another square root. So I've got a square root under a square root. And again, the first thing we see under that square root is n, which is 10. And then times the sum of the y squareds. The sum of my y squareds is this guy right here. And so that's 3,775,842, I'm running out of space, 0.76. And then that needs to have the sum of the y quantity squared subtracted from it. Well, the sum of the y was 5,554, so I need to take and subtract that number squared. Holy cow, right? Now, if you do this with me on your calculator and pause the recording a moment, when you calculate the numerator portion of this correlation, just take 10 times the 15,000 number minus 23.1 times 5,554 and hit enter. Your numerator portion should equal 27,439.7. That then needs to be divided by the denominator. So the denominator is the first square root has a value equal to 139.89. And sorry, I misspoke earlier. It's not a square root within a square root. It's a square root times a square root. The second square root, if you calculate it with me, should have a value of 6,911,511.6. Now, if you take and calculate the numerator and divide by the denominator, if you're going to do this all in one command, remember to put that denominator in parentheses. You should get a correlation about equal to 0.882. And that basically suggests that there's a pretty strong positive linear association. Positive because its value is positive, and it's pretty strong because it's relatively close to 1. So we can say that as the gross domestic product increases, there appears to be a relationship such that the carbon dioxide emissions also increase with it.